Hello everyone, welcome to another session with PTV Leadex Education, your educational biome of pure excellence and extremely high quality. So in our lesson of today, we are going to be discussing about a wonderful process in chemistry called hybridization. Hybridization. Yeah, this is a very wonderful and a very powerful concept in chemistry or organic chemistry. So hybridization simply has to do with the formation of covalent bonds, right? It describes the microscopic level or the microscopic process by which covalent bonds are formed. So let's begin by explaining why bonds are formed and what are covalent bonds. So typically, when, for example, we have carbon, right, reacts with oxygen, right, is going to form carbon dioxide. Carbon reacts with oxygen to form carbon dioxide. Here, carbon does not have the octet structure. Carbon does not have the octet structure. And as a result, carbon will go into bonding with oxygen so as to form covalent bonds. Carbon dioxide has a linear shape in which both atoms attain the octet structure of the noble gases and are very stable, right? So compounds or elements form bonds in order to become stable, in order to attain the octet structure or the duplex structure of the stable elements, typically the noble gases. And when atoms go into bonding, right, the process by which they form covalent bonds is called hybridization. Yes, generally at the ordinary level, when they ask us how are covalent bonds formed, right, we say that covalent bonds are formed by the sharing of electron pairs. Covalent bonds are formed by the sharing of electron pairs. That is the reply of an ordinary level student. But at the advanced level, a much better reply or a more mature reply is that covalent bonds are formed by the process of hybridization. Covalent bonds are formed by what? The process of hybridization. Covalent bonds are not formed by the sharing of electrons at the advanced level, but covalent bonds are formed by what? The process of hybridization. Yes, that is the process by which covalent bonds are formed. Now, before we even talk about that, what is a covalent bond, right? Most of you guys don't even know how to define these bonds. So what is a covalent bond? A covalent bond simply is the electrostatic force of attraction that exists between the positive nuclei of the bonded atoms and the shared pair of electrons. That is a covalent bond. A covalent bond is the electrostatic force of attraction that exists between the positive nuclei of the bonded atoms and the shared pair of electrons. So for example, let's consider two atoms, right, X and Y. So this is our bond. For example, let's consider a basic atom, right? Anyway, let's consider two atoms, X and Y. This is the nuclei of one atom, right? And this is a valence shell. So this nuclei is going to share an electron pair with another one, right? This is an electron pair that they share, and these are their nucleus. So we all know electrons are negative, so there is a negative charge, right? There's a negative charge inside here, right? Electrons are negative, so there's a negative charge here. And how is the nucleus? The nucleus is positive. The nucleus is positive. So the negative electrons and the positive nucleus experience what? Electrostatic force, right? Electrostatic force exists between charged bodies. So the nucleus is positive and the electrons are negative. So automatically there will be electrostatic force between what? Between the positive nuclei of the bonded atoms and what? The shared pair of electrons. That electrostatic force is called a covalent bond. So that is how you define a covalent bond, as the electrostatic force of attraction that exists between the positive nuclei of bonded atoms and the shared pair of electrons. And as we earlier said, covalent bonds are formed by what process? The process of hybridization. So let's go ahead. What is hybridization? What is hybridization? Hybridization simply is defined as the mixing of pure atomic orbitals to form molecular orbitals of similar energy or of the same energy called hybrid orbitals. Hybridization is defined as the mixing of pure atomic orbitals to form molecular orbitals of the same energy called hybrid orbitals. That is how you define the wonderful process of hybridization, through which covalent bonds are formed. What is an atomic orbital? Right? For us to understand hybridization, let's look into what atomic orbitals are and what are the basic ones. So, as we all know, an atomic orbital is defined as the region of space around an atom, right? The region of space. An atomic orbital is the region of space around the nucleus of an atom where there is the highest probability of finding an electron. An atomic orbital is what? It is a region of space around the nucleus of an atom where there is the highest probability of finding an electron. That's because it is in the atomic orbital where electrons are what? Residing, where electrons are located. So that is a region around the nucleus where you have the highest chance of ever meeting an electron. So, as atomic orbitals are of different types, right? We have the s orbital, the p orbital, the z orbital, the f orbital. These are the basic or the basic ones, right, at this level. So the s, the p, the z, and the f. These are pure atomic orbitals. These orbitals are called what? Pure, right? They are natural, right? They are pure atomic orbitals. When these orbitals will overlap, when these orbitals mix up, when they mix up, what do? They form new orbitals called what? Hybrid orbitals, in a process called what? Hybridization. When these orbitals mix up, as we said, hybridization is what? The mixing of atomic orbitals, of pure atomic orbitals, to form molecular orbitals of the same energy called hybrid orbitals. Right? So when the s and the p or s and z or these orbitals just mix up at random, what do they form? They form new orbitals that have the same energy. Now, the energy of orbitals decreases as the orbital is away from the nucleus, right? Orbitals are around the nucleus. This is a nucleus, right? So, as we know, electronic configuration, we have what? We have 1s1, 2s2, 2p6, 3s2, 3p6, 3p6, 4s2, 3z10, right, etc. That is how we write electronic configuration. As the more, right, these values, this is a first shell. This is a first shell. When the quantum number n gives it the shell number, 22 represents the second shell, 3 represents the third shell, while the 4 represents the fourth shell. So the more the shell number, this is a nucleus, first shell, second shell, third shell, and so on, right? The more the shell number increases, the lower the energy of the more the shell number, right, increases, yes, the greater, right, the greater, not the lower, please, the greater the energy of the orbitals, right? The more shell number, that means that the shells which are closer to the nucleus, right, they have lesser energy, right? Because the energy levels, right, you all know of the hydrogen emission spectra, yes, and the energy level increases the more the energy value increases to what? To 0 at the infinity, the more we move away from the nucleus. So these orbitals, they have different energies, right? They have different energies. And when they mix up, what do? They form new orbitals that have the same energy. that have a common energy. Those new orbitals, we call them hybrid orbitals. Now, when hybridization occurs, what is formed? What is formed? Right? Covalent bonds are formed, and covalent bonds are of two particular types, right? Two particular types. Not simple and dative, no. Those are also types, but what we are referring to here are the two special types of covalent bonds. And those two special types are sigma bonds and pi bonds. Yes. When atomic orbitals overlap, when hybridization occurs, new orbitals of the same energy are formed, called hybrid orbitals. Now, when hybrid orbitals undergo overlapping, undergo what? Overlapping. Undergo what? Overlapping. Overlapping. When hybrid orbitals, what we are saying, when atomic orbitals, right? When atomic orbitals, the pure, that is the S, the P, the Z, the F, etc. Right? When atomic orbitals do what? They mix. When they mix randomly, when they mix, right? When they mix. So when they do what? When they mix. This is mixing. When atomic orbitals mix, what do? They form new molecular orbitals called what? Hybrid orbitals. So they form here hybrid orbitals. And what is a major feature of hybrid orbitals? Hybrid orbitals have what? They have the same energy. Yeah, they have the same energy. Now, when hybrid orbitals do something, the hybrid orbitals must do something, because we say that covalent bonds are formed by hybridization. Yes. And hybridization is this process. But something else must happen for us to have the final covalent bond. So the hybrid orbitals are going to do something further. And that thing is called what? Overlapping. Overlap means that you come together. Right? You come together. Either like this or like that. You overlap, you mix. Not like you mix, but you approach each other. Yes, you fall on each other, not mixing. So when hybrid orbitals do what we call overlapping, when they undergo overlapping, what do? They bring what we call covalent bonds. They now form the actual covalent bonds. And the actual covalent bonds are of two types: sigma bond or pi bond. Right? So the overlapping of hybrid orbitals as well as atomic orbitals. This overlapping can take place between hybrid orbitals only, or between hybrid orbitals as well as unhybridized orbitals. That means that, look at orbitals here. For example, if S and the P mix up, they will form SP. Right? They will form SP. If P orbitals mix up, right, then they will form P and S have to mix up. If S and P orbitals mix up, then they will form SP orbital. They will form SP. That SP is not a normal orbital. It's not a pure orbital, but it's a hybrid orbital formed by the coming together of what? Of S and P. If SPZ mix up, what do they form? They form SPZ orbital. It is neither S nor P nor Z, but it is what? It is SPZ, right? SPZ orbital and so on. So when these hybrid orbitals overlap with pure orbitals, they will form what? Covalent bonds, right? When these hybrid orbitals overlap within themselves, what do they still form? They form covalent bonds. And those covalent bonds have two different types. They are either sigma bonds or they are pi bonds. Or they are what? Pi bonds. Yes. So sigma bonds and pi bonds are formed by what? The overlapping of atomic orbitals. So at this level, there are two types of covalent bonds formed through hybridization: sigma bonds and pi bonds. How are they formed? They are formed by what? The overlapping of atomic orbitals and or hybrid orbitals. Sigma bonds and pi bonds are formed by what? The overlapping of what? Atomic orbitals and or hybrid orbitals. What do we mean there? We mean that if hybrid orbitals overlap, if they overlap head-on or lateral, what do they form? They form sigma or pi bond. If hybrid orbitals overlap, if unhybridized, these orbitals here are unhybridized, right? They have not gone hybridization, so they are unhybridized. So if pure atomic orbitals overlap head-on or lateral, they will still form what? Sigma and pi bond. So those are the two types of covalent bonds formed by hybridization. Now, we are going to look at how sigma bonds and pi bonds are formed, right? How sigma bonds and pi bonds are formed. So before that, let's look at the structure of s and p orbitals, because at this level we shall limit ourselves to hybridization that only involve the s and the p orbitals, right? The d and the f shall be seen at the higher level, that's the university level. But for now, we shall look at the s hybridization that involves s and p orbital. So an s orbital has this shape, right? This is the shape of an s orbital, like this, and it has a nucleus, right? It has a nucleus. Yes, a nucleus. Then, as we said, an orbital is a region of space around the nucleus of an atom where there is the greatest probability of finding an electron. So this is the shape of an s orbital, right? This one here is a nucleus, right? Now, a p orbital has this shape, right? And this is its own, well, my diagram is not balanced. A p orbital has this shape, right? This is its own nucleus here, right? And then inside there we have at least one electron. Sometimes we can have two electrons. Yes, inside here, right, we can have one electron or two. Two electrons is a maximum for what? A suborbital, right? A suborbital like the s holds a maximum of two electrons. So here are the nuclei of the orbital. So this one here, this is a structure of a p orbital. A p orbital. Yes. So sigma bonds, right? Let's take the first one. Sigma bonds. How are sigma bonds formed? Right? Sigma bonds. Sigma bonds. Right? And then here we have pi bonds. Please, pi bond, sigma bond. Pi bond, sigma bond. So what are sigma and pi bonds? Sigma and pi bonds are the two types of covalent bonds that result from the process of hybridization of atomic orbitals. Sigma and pi bonds are the two types of covalent bonds which are generated through the process of hybridization of atomic orbitals. So they have their specific ways in which they are formed, right? They have their specific ways in which they are formed. The easiest of them is a pi bond, the pi bond, right? The pi bond. So the pi bond has only one method of formation. The pi bond has only one method of formation. But before you know how they are formed, the first thing you must note here is a distinguishing nature of their formation. Sigma bonds are formed only by what? The head-on overlap of atomic orbitals. What did I say? Sigma bonds are formed only by what? The head-on overlap of atomic orbitals. So here we have what? We have head-on. We have head-on overlap. Or you say head-to-head. Head-on overlap. Or you say head to head, head to head, head to head overlap. That is how sigma bonds are formed. This is very fundamental. To avoid all confusions, remember, sigma bonds are formed by what? The head-on overlap of what? Orbitals. Those orbitals can involve what? Hybrid orbitals as well as unhybridized orbital. Now, how are pi bonds formed? Pi bonds are formed by the lateral overlap. Lateral only. Pi bonds are formed by what? The lateral overlapping. The lateral overlap of what? Of 2p orbitals. Lateral overlap of 2p orbitals. That is the only method by which sigma bonds are formed. Sorry, by which pi bonds are formed. Pi bonds are formed by the lateral. Lateral means that the p orbitals come like this. One, right? As you can see, this is a p orbital. When one p orbital, right, merges like this, these are their nucleus. When they overlap laterally, how does it go? This side, right, will come in closeness. Lateral is like this. Lateral means that I stand here, you stand here. Our heads come together. Our legs also come together. So lateral. Head on means that what? We come like this. We come like this. That's head on. Head on is for what? Is for sigma bonds. Lateral is for what? Is for pi bonds. So pi bonds, for the pi bond, this is what you're going to have. Right, like this. So the overlapping is here, right? Is here, like that. But my diagram is not really showing explicitly. Right, let's put it again. Like that. This is at the nucleus. Then the overlapping, right? The lateral overlapping is here. That is how so this one here is what? This is a pi bond. That's a pi bond. So how is a pi bond formed? The lateral overlapping. Never forget that. What did I say? Pi bonds are formed by the lateral overlapping of atomic. Oh, no, sorry, not atomic, please. The lateral overlapping of what? 2p orbitals. Only. What did I say can overlap? Let's summarize it. We said that orbitals which can overlap are what? Hybrid orbitals. Hybrid orbitals. Hybrid orbitals are those formed from what? Hybridization, right? They can overlap. But what can also overlap? Unhybridized or pure atomic orbitals. Pure atomic, or you call them unhybridized. That means that orbitals that have not gone in hybridization. Unhybridized what? Orbitals. Right? Hybrid orbitals can overlap. Those formed from what? Hybridization. Or pure atomic or unhybridized. That means that the original natural orbitals, they can also do what? Overlap. Voila. And what can also overlap here? But this pure atomic or unhybridized, right? We can talk of an s orbital, right? S orbital is also pure atomic and also a p orbital. Yes. So how are pi bonds? These are the different types of orbitals which can undergo overlapping to produce sigma and pi bonds. Now, for pi bonds only have to do with what? The lateral overlapping of what? Of p orbitals. Of p orbitals only. That means that what? S orbitals, hybrid orbitals, pure atomic orbitals are not involved in what? In pi bond formation. Pi bond formation only involves the lateral overlapping of P of 2P, 2P, 2P only, no S. 2P, no hybrid, no hybrid. Only what? Only 2P. For pi bond to be formed, you need what? You need only p orbitals, nothing else. P orbitals only, right? Only pure p orbitals that you need to form pi bonds. And how do they overlap? Laterally. Sigma bonds are formed now by the head-on, no lateral, head-on overlap of what? Of any of this mixture. This combination of mixtures will give us 5 different methods by which pi bonds are sigma bonds are formed. Pi bonds, one method only, lateral overlap of p orbitals. Sigma bonds have 5 different methods of formation. All the 5 methods involve what? The head-on overlap. The head-on overlap of what? Of different combination of orbitals. Now, what are those different combinations? The first one, a sigma bond can be formed by the head-on overlap of 2 s orbitals. That means that an s and let's write here, an s and an s, right? The head-on overlap of 2 s orbitals. That means that 1s, they overlap head-on. What will they form? They will form a sigma bond. Second method, sigma bonds are also formed by the head-on overlap of an s and a p orbital. Or better still, 2 p orbitals. That means if a p orbital overlaps head-on with another p orbital, what do they form? They form a sigma bond, right? Next, a sigma bond can also be formed by the head-on overlap of an s orbital and a p orbital. That means that an s comes, a p comes, they overlap head-on. What do they form? A sigma bond. So a sigma bond also involves an s orbital with a p orbital going into head-on overlapping. Next, a sigma bond can also be formed by the head-on overlap of what? 2 hybrid orbitals. 2 hybrid orbitals. That means that here, 2 hybrid orbitals. So if a hybrid orbital merges or overlaps head-on with another hybrid, what do they form? They form a sigma bond. Next, a sigma bond can also be formed by the head-on overlap of a hybrid orbital and an unhybridized orbital. A hybrid comes with what? An unhybridized or a pure atomic, and they overlap head-on. What do they form? A sigma bond. So you can also have a hybrid orbital overlapping with an unhybridized orbital. It produces what? A sigma bond. So these are the 5 different methods by which sigma bonds are formed. 1. Head-on overlap of 2 s orbitals. 2. Head-on overlap of 2 p orbitals. 3. Head-on overlap of an s and a p orbital. 4. Head-on overlap of 2 hybrid orbitals. 5. Head-on overlap of a hybrid and an unhybridized orbital. That is the formation of sigma and pi bonds. So guys, we are going to stop here for the moment. I hope that you had a good understanding of sigma and pi bonds. In our next lesson, we are going to come to see how to count the number of sigma and pi bonds in a molecule. And we shall also compare the strength of sigma and pi bonds. I'm sure you have been told that sigma bonds are stronger than pi bonds. But here, we are going to enumerate the two reasons why sigma bonds are actually stronger than pi bonds. And from then on, we shall discuss sp, sp3, sp2 hybridization in carbon and illustrate them graphically. So guys, please like the video. Please, if you have not pressed the like button, press it, I beg, right? Like the video, share the video, and put it in your favorite, because you surely need it next time again. So like the video, share the video, and invite your friends to follow PD Leadex Education. You can follow us on YouTube, on TikTok, as well as on Facebook. Follow Leadex, and the best is yet to come. God bless you, and thank you so much.